Hello, I'm Haba Bahir. In this presentation, I will talk about the nuclear size radius and how we calculate it. How small is the nucleus of an atom? That's really. Rutherford scattering experiments. The first estimates of nucleus size come from the Rutherford scattering experiments. So Rutherford and his team, they pumped alpha particles into a gold foil. And they saw that the vast majority of these alpha particles went through the gold foil and divided, while few of these alpha particles experienced deviation. And even fewer alpha particles experienced division at completely backwards angle of 180 degrees. This suggested that the vast amount of the matter contained within gold foil or in the atom of the gold foil was concentrated in a very tiny region. Following these kind of experiments, Rutherford gave his much famous planetary modeling, which is suggested that the vast majority of the matter of an atom is contained in a very small region inside the atom, which is at the center of that, which is known as the nucleus. According to the Rutherford's estimates, the size of the nucleus was even smaller. It's around 10 to the power minus 12 centimeters. Now, this is a very small number. And since that point in time, we have developed much more precise methods of measuring the size of a given nucleus of an atom. And according to current estimates, for example, if you look at the hydrogen atoms, the hydrogen atoms has a nucleus which has a radius 0.8 ferrometers, and 1 ferrometers is equal 10 to the power minus 15 meters. The radius of hydrogen atoms is equal 0.5 angstrom, and it's equal 50,000 ferrometers. So let's make a comparison between the size of the nucleus and the size of the atom itself, and see how big the atom really is compared to the size of the nucleus, or how small the nucleus really is compared to the size of the atom. So if I make a comparison, the hydrogen atom has size of around 0.5 angstrom, which is nothing, but approximately 50,000 centimeter range of implement is a standard minus 15 meters, and angstrom is 10 to the minus 10 meters. So if I convert it become 50,000 from 2 meters. So if I find the ratio between the atomic size and the nucleus size, if I divide the atomic size, which is the radius of the hydrogen atoms, with the nucleus size, which is the radius of the hydrogen nucleus, then what sort of the number should I get? So this comes out be around 50,000 divided by 8 ferrometers, which give us approximate value 62,500. That's a huge number. So the hydrogen nucleus is 62,000 times smaller than the atom itself, or rather, the nucleus has a radius which is a distance of 62,000 times smaller than the distance and which the electron of hydrogen atoms exists far away from the nucleus. Now, let's do a little bit of a fun sort of comparison between this kind of ratio that exists between the hydrogen atom size and the nucleus size with some other physical example. So here I have, let's suppose, a golf ball, and I have measured the radius of the golf ball to be around 2 centimeters. Now, if I imagine that this golf ball is the nucleus of the hydrogen atom, then what should be the size of the hydrogen atom itself? Or how far? Should the nearest electron have that kind of hydrogen atom nucleus should be from this point? So, if this golf ball has, let's suppose, a radius of 2 centimeters, right? Then if I multiply this with this ratio, it's 62,500, then this come out be 1.25 kilometers. And that's mean the nearest electron have this kind of hydrogen atom nucleus would be 1.25 kilometers far away from it. Can you see what I'm talking about? Now, since the time of Rutherford famous scattering experiments, many more precise methods were developed over time to calculate the nuclear radius much more precisely. To measure the radius of a nucleus. I have listed some of this method here, but to understand these methods, let's understand that things here. The nucleus is consisting of two kinds of particles, protons and neutrons. Protons are positively charged particles which interact with their Coulomb field. Neutrons are in neutral particles which do not interact with the Coulomb field. So all kinds of different methods can be classified into two parts. First of all, where there are certain kinds of experiment which basically tries to interact with the Coulombic field of the nucleus, and second, there are certain kinds of experiment which don't interact with the Coulombic field of the nucleus. So whenever the experiment involves Coulombic interaction, that experiment basically gives us an idea about the charge distribution or how the protons are distributed in the nucleus. And whenever some kind of an experiment does not involve Coulombic interaction, it basically gives us an idea about the nuclear matter distribution. The experiment which tell us about the charge radius of the charge distribution we call it EM methods, and there's here. And the experiment which tell us about the nuclear matter distribution or the nuclear matter radius, which is called nuclear method. It's like here as alpha decay and bimasonic X-ray. In this video, I don't want to go into detail in this experiment. If you are interested in knowing more about this experiment, you can research in Google. One very important conclusion that came about from the different kind of experiments that were performed over time was that the nuclear matter distribution and the nuclear charge distribution had approximately the same radius. It's not like protons are concentrated in the center and the neutrons are spread out over the surface, and it's not like neutrons are concentrated in the center and the protons are spread out of the surface, as soft like that both protons and the neutrons are uniformly distributed throughout the volume of the nucleus. This is the reason that charge and the nuclear matter radius is approximately equal. There is another important thing that we need to understand. First of all, even though we are talking of a nucleus as if it is a spherical object, the nucleus is not necessarily a spherical object. I mean, most nuclei are just basically aggregates or collection of smaller nuclear particles like protons and neutrons, and most of this collection in certain cases makes not necessarily symbol of a sphere. And many times this kind of nucleus does not have a sharp boundary either. But for the sake of convenience, we do assume the nucleus to behave as a sphere and to have a sharp boundary. And that's why we speak of radius, because radius can only exist of sharp boundaries, but the boundaries are not necessarily sharp. And this is important to keep in mind. The reason we do this for the sake of convenience, so that we can gather some information about the nucleus, and to understand this more, let's look at the sort of a charge distribution that is obtained from the different kind of experiment. So let's look at this diagram first. So here is a representation of how the nuclear density change as you move from the center of the nucleus outwards. Now there are some very important takeaways from this kind of graph. First of all, as you can see, as I just now told you, the nuclear density falls along a slope near the surface of the nucleus. That means the nuclear surface does not have a sharp boundary, or the nucleus doesn't have a sharp boundary, but rather the density change over a slope gradually over a certain amount of distance. Now, there are different kinds of parameters associated with this kind of slope. So for example, if you looked at the density, if you calculated density if you calculate the region where the density is around 90-100%, of its maximum value, then it's 0.9 rho. And if you calculate the distance at which the density is around 1000% is a maximum value, so it's 0.1. Then these two distances are separated here. Yeah, it's separated, but what is known as skin thickness. So this skin thickness is basically the distance over which the density decreases from 90% of its value to 10% of its value. And if you look at the point at which density reaches 50% is value, so this here, so this is around 50% the density, then this point is known as, basically it will mean sort of a radius, mean radius. So basically, since nucleus don't have a sharp boundary, so whenever you talk about radius, you either talk about the mean radius or the root mean square radius is calculated from the experimental data. Now, this kind of chart distribution tells us that, first of all, the nucleus doesn't have a sharp boundary, and second of all, and very importantly, that the density is constant almost throughout the entire volume of the nucleus. If you look at the density is constant throughout the volume of the nucleus. It only drops near the surface beyond in the inner body. It remains almost constant. Now, this is a very peculiar property. Let me just give you an example. If you look at the Earth as a planet, if you start digging a hole and you keep going towards the bottom or towards the center of the Earth, you will find that the density of odd keeps increasing. The pressure keeps on building up as you go downwards, and the density of the matter also keeps on increasing. The density at the center of the Earth is extremely huge. Why is it so being? It's so because of a gravitational force. Gravitational force is a central force field. It attracts all the matter particles toward a particular center, and therefore, as you go toward the center, the density keeps on increasing. However, whatever force is acting to hold the nucleus together is a little bit different, in the sense that if you go toward the center of the nucleus, the density of the nuclear particles does not increase. So if you go toward the center of the nucleus, the density of the nuclear particles in the center is similar to the density of the nuclear particle almost near the surface. The particles are all equidistant to each other in a manner that the density is constant throughout the nuclear volume. This tells us something very peculiar about the nature of the force that holds this kind of nucleus together. So the force that holds this kind of nucleus together is a strong nuclear force, or the nuclear force. And the nuclear force is not a central force. It is a force which acts not only between neutrons, it also acts with the neutrons and protons. Also, it creates a situation where all particles inside the nucleus are at constant density. Now, this gives us a way to calculate the radius of any given nucleus. So, for example, if the density of a nucleus is constant, in that case, density is just mass of the nucleus divided by its volume. So instead of a mass, let me just write now the mass number, because more the number of the particles, more the number of the neutrons and protons, more is the mass of the entire nucleus. The mass number divided by the new volume, which is 4 by 3 by our huge R being, the approximate mean radius of this kind of a nucleus is basically equal to constant. This is something that we can see from the experimental data, or that the graph that we have in previous slides. Now, what can we conclude from this relation? Since this is a constant And here are two variables, mass, number A, and radius. This is a proportional that exists between A and R cube, which basically is our R cube is directly proportional to A. So R cube is directly proportional to the mass number. This basically means that the volume of the nucleus is directly proportional to the number of particles that are contained within it. So basically gives us a way to calculating a radius of any kind of given nucleus. This leads to a relation where R, our radius, is equal R naught multiplied with A to the power 1 over 3. So as you can see here, R naught is constant of proportionality, and the value of our naught has been experimentally determined to be approximately equal to 1.2 ferrometers. So now, if you know the mass number of even apps of an element, can calculate its radius. A few takeaways from this presentation. First of all, the nucleus is an extremely tiny object, as we saw in the beginning of the video. Second of all, the nucleus does not have a sharp boundary, but rather the boundary sort of diffuses over a period of a distance. Third of all, the density of the nucleus is constant, almost through the entire volume of the nucleus, which tells us a lot about the nature of the force that is acting inside the nucleus itself. And lastly, we have obtained the relation of finding the radius of any given nucleus by knowing just its mass number, where we know that the radius of the nucleus is directly proportional to the cubic root of the mass. Now, that is all for today. I hope you enjoyed the video. Thank you for listening, and bye.